Hello, students. Uh, if I sound tired during this particular lecture, it's because I am. It's getting to be a long day of trying to get these out, so I'll try to keep my energy level as high as I can. Um, let's talk about what we're going to do today. So, what we've done so far in terms of, say, the unit circle and understanding trig functions is we figured out how to evaluate trig functions at some particular points. And let me go ahead and pull up what we have done. Okay, we are back. Uh, so what we did last time is we used right triangle trigonometry in order to fill in some entries in the unit circle. We know that the trig functions cosine and sine corresponding to pi over 6 satisfy that cosine is root 3 over 2, sine is 1 over 2. But this is a circle. It's the most symmetric object you can think of. So we should be able to say, if we understand this point, we should be able to understand that point. That's what we'll do today. Not only will we fill in the rest of this unit circle, we'll learn some properties of trig functions. So let's go ahead and get started. So here are the properties that we'll try to establish. For any integer k, we'll try to figure out what adding 2 pi k to an angle does to trig functions. We'll try to figure out what subtracting an angle from 2 pi, or just sticking a negative sign in front of that angle does to trig functions. We'll try to figure out what doing pi minus an angle, pi plus an angle, pi over 2 minus an angle, and pi over 2 plus an angle, what all of those do to trig functions. Well, let's get started. And this is the order in which things will happen. So let's get started. Let's think about an angle of theta plus pi plus 2 pi k. Well, let's think of it this way. For any integer k, 2 pi k radians corresponds to what sort of angle? Well, it corresponds to 2k full revolutions. So if you want to understand an angle of theta plus 2 pi k, you can understand it by forced rotating by k full revolution. So spin all the way around the circle k times, and then additionally by theta radians. Do those full revolutions affect the end location? Of course they don't. Just spinning around the circle a bunch of times, you wind up back where you started after each full revolution. So that means that the x and y position after you do a rotation by theta plus 2 pi k radians is the same as if you just rotated by theta. So that means cosine of theta plus 2 pi k is the same thing as cosine of theta. Secant is the same as secant theta. Tangent is the same as the tangent of theta, because all of these are determined by the point where you land, and that point didn't change. All right, so there's the first result. It's pretty easy. So let's just put that on that cover page. Next, let's think about this sort of angle. Well, let's draw a picture to figure it out. This one's going to actually have some content. Here's an angle of theta. So I've started at 1, 0. I've rotated forward by an angle of theta. I landed at cosine theta comma sine of theta. If I want to understand what happens when I plug in negative theta, well, negative theta will correspond to rotating backwards by an angle of theta. Or if you prefer, that's the same thing as going all the way around the unit circle and then back by theta. So that's why this angle of negative theta should correspond to the same point as 2 pi minus theta. If you like, 2 pi minus theta is the same as negative theta plus 2 pi. So those two should have the same xy coordinates. Well, look at these two pictures. On the one, I start at 1, 0 and I rotate up. The other one, I start at 1, 0 and I rotate down. What sort of symmetry relates these two pictures? Well, reflection across the x-axis. What does that do to coordinates? Well, let's see, reflecting over the x-axis preserves x coordinates. So that means that this x coordinate is the exact same as that x coordinate. So cosine of theta is the exact same as the cosine of negative theta. The y coordinate, on the other hand, is not preserved. The y coordinate gets negated, as in a negative sign shows up in front of it. So here, this y coordinate and that y coordinate are exactly the opposite of each other. So that means that the sine of negative theta is exactly the same as negative the sine of theta. That's right. This y coordinate is sine of negative theta is exactly the opposite of negative the sine of theta. Oh, so I guess saying this again, cosine of negative theta is the new x coordinate. I'll continue writing that in green. That's the same thing as the original x coordinate, but that's cosine of theta. Sine of negative theta is the new y coordinate, but the new y coordinate, when you do the symmetry, becomes exactly the negative of the old y coordinate. And the old y coordinate, that's just sine. So, filling in lines on that cover page, cosine of negative theta is the same thing as the cosine of theta. The sine of negative theta is the same thing as negative the sine of theta. And those are some facts worth remembering. Now maybe another way of seeing it is, maybe I'll write this right here. This manipulation, replacing an angle by negative theta, that corresponds to reflection over the x-axis. So the x-coordinate cosine is the x-coordinate, should stay the same. The y-coordinate sine should become negative. Cool. So let's keep on going. I won't get through all of them, all of these manipulations, but I'll get through some of them. And then I'll post another video, right? You understand how I'm doing things. I think I have an established pattern. So let's use these. So cosine of negative theta is the same thing as cosine of theta. Sine of negative theta is the same thing as negative the sine of theta. And now, well, if we know sine and cosine, we know all of the trig functions. So let's talk through all of these trig functions. If this were in class, what I would do is I would do one of them, have you guys do one of them, and then I'd write down the result for the rest. So I guess what I'll do is I'll do one of them. Yeah, I'll do two of them, and then I'll write down the result for the rest. You guys should pause this video if you want to, and figure out how all of these trig functions change. So let's do that. Maybe I'll start from the start, secant. So let's try to compute the secant of negative theta. Let's see, the secant of an angle is the same thing as 1 over cosine, so secant negative theta is 1 over cosine of negative theta. But I know what happens to cosine when I stick a negative sign. Cosine of negative theta is exactly, cosine of negative theta is the same as cosine of theta. So I can replace cosine of negative theta with the cosine of theta. So that means secant of negative theta is the same thing as cosine of theta, but cosine of theta, well, that's the same thing as secant theta. And maybe just in interest of doing one where it does actually change, let's figure out the same thing for cotangent. Let's compute cotangent of negative theta. Well, what is cotangent? Cotangent is cosine over sine. But, right, the thing inside of the parentheses is negative theta, so it should be cosine of negative theta divided by sine of negative theta. Well, I know what cosine of negative theta is, right? Cosine of negative theta is the same thing as cosine of theta. Sine of negative theta is negative sine theta. Well, I see a negative sign just in the denominator. I see x divided by negative y. So I can pull that negative sign out of in front of the fraction. So I'll get negative cosine theta divided by sine theta. Oh, but cosine divided by sine, that's cotangent. So cotangent of negative theta is negative cotangent theta. And let me just fill in the rest of these. Cosecant of negative theta will be negative cosecant theta. Tangent of negative theta is negative tangent theta. Neato. So in order to see an example of this moving information around, let's use it to do some computations. So I won't tell you why this is true until later in the class, but it turns out that the cosine of pi over 8 is equal to the square root of 2 plus the square root of 2 all over 2. And right, if you just heard me say that out loud, you don't know where the parentheses go. So if you're watching these videos by just listening to them, now is the time that you actually have to take a look in order to see where the parentheses belong. So let's use those results to compute other trig function, the sine and cosine rather, at angles that are like similar to pi over 8. Well, let's start with the cosine of negative pi over 8. Well, that's literally cosine of negative an angle. And I know what happens when you stick a negative sign in front of an angle in a cosine. Nothing. This is the same thing as the cosine of pi over 8. And, well, I know what cosine of pi over 8, well, right, know is a weird word to use here. So I think a good definition of to know something is it's something that you believe and is correct and you have a good reason to believe it. And it is correct. This is what cosine of pi over 8 is. Maybe you believe it. Is it a good enough reason for you to believe it that I just tell you it's true, though? So I don't know if it's knowledge. But whatever, that's tangential. Neat. Let's think about the cosine of 17 pi over 8. So that is the same thing, if you notice, as the cosine of 16 pi over 8 plus pi over 8, also known as the cosine of 2 pi plus pi over 8, because 16 pi over 8 is exactly 2 pi. But I know what happens when you do cosine of 2 pi plus an angle. Nothing. You get the same output. So you'll get the same thing as the cosine of pi over 8, also known as the square root of 2 plus the square root of 2 all over 2. Nice. So let's do one more thing with this. No, actually I can't. Yeah, I can do something with this. On the unit circle to the right. So let's try to fill in some entries in that unit circle. Where is it? There it is. Let's try to figure out trig functions at 11 pi over 6, 7 pi over 4, and 5 pi over 3. So let's try to compute cosine of 7 pi over, 11 pi over 6. So notice, that's the exact same thing as the cosine of 12 pi over 6 minus pi over 6. So all I did there is I noticed that, 11 pi over 6, that's really close to being 2 pi. So let's write it as 2 pi plus or minus a little bit. And that's what you get. Proceeding. That gives us cosine of 2 pi minus pi over 6. And I know what happens there. I get the exact same thing as I started with. It's the same as cosine of pi over 6. Looking at this unit circle, pi over 6, cosine is the x-coordinate, you get root 3 over 2. Let's try to do the same thing for sine, and then I'll fill in the rest of them without doing the walk. If you want to compute the sine of 11 pi over 6, similarly, that's the sine of 12 pi over 6 minus pi over 6. So that's the sine of 2 pi minus pi over 6. And I know what happens when I do 2 pi minus an angle. Sine of 2 pi minus an angle is exactly that same, is negative the sine of that angle. So sine of 2 pi minus pi over 6 is the same thing as negative the sine of pi over 6. But I know what the sine of pi over 6 is. Go forward by an angle of pi over 6. We read the y-coordinate. The y-coordinate is 1/2. So I wind up with a negative sign because of that negative sign. And the y value was 1/2. Neato. And for the rest of these, you can do the exact same argument. To compute trig function at 7 pi over 4, think about trig function at pi over 4. You'll see that you get root 2 over 2, negative root 2 over 2. Trig function at 5 pi over 3, well, that's 2 pi minus pi over 3. So this point should be the exact same as that point, but reflected over the x-axis. So I'll get 1 over 2, negative root 3 over 2. Nice. I'm going to stop there. I don't think I have that much more energy left in me today, so it'll be tomorrow before I record any more videos. Great. I'll talk to you later. Enjoy.